Hello, everyone, and thanks, Adam, for the introduction. Today, I will be talking about hybrid digital twins, and in particular, the application of this technology to predictive maintenance and prescriptive maintenance of heat transfer equipment. So, heat exchangers, heat exchanger networks, and so on. In particular, I would like to put things in perspective in terms of Industry 4.0 and how heat exchangers fit within the Industry 4.0 revolution, and how digital can really help maintenance of heat exchanger networks, which are extremely important for the profitability of any plant. So Industry 4.0 does give us a world of opportunities. I think this audience knows this very well. We're already using drones to inspect our plants. We are using Internet of Things to connect various parts of our plants and various pieces of equipment. Virtual reality is being used with mixed reality for better training of operators. And we are 3D printing already parts. If you talk about more in general, not just in our industry, the US Navy, for example, is already 3D printing parts of their ships so they can not have to go back to port for a longer time. So it's really a very big opportunity. But I cannot tell you how much I can't wait to see our plans to be AI run, IoT connected, drone surveilled, robot maintained, environmentally friendly, safe, and profitable. However, we need to go back to reality, and the reality of things is that our assets are old. Maybe not this old, but they're old. So if you look at data for the Netherlands, for example, there are over 50% of installation are older than 20 years, and over 30% are older than 30 years. So what does that mean? Well, that means two things. One is that the plants that we are running were not designed for this type of technologies. So it makes it challenging on one hand to run very advanced technologies and collect enough data to run, for example, artificial intelligence. But on the other hand, it also means that maintenance, it becomes key for the safe operation and profitability of our plants. And in fact, this is a survey from Accenture a few years back now, that they ask where is digital having the most positive impact in refineries, and over 56% of the respondents to the survey indicated that maintenance and reliability was the area that already was giving the most positive impact. So there is really a significant opportunity to apply digital to our plants, even if they're aging, particularly if they're aging, but there are challenges associated with it. So what about heat exchangers? We've seen the Industry 4.0 revolution is on its way, but what about this critical piece of equipment? So heat exchangers are ubiquitous in our plants, and they are used for heating and cooling needs. They are key for energy recovery. So we can unlock through the use of heat exchanger networks, for example, we can unlock significant savings and reduction in CO2 emissions because we can decrease the energy requirements, the heating requirements, for example, in the process. But they can become a bottleneck for production, as I show in a minute in a few slides. In certain cases, they are vital for the integrity of mission-critical components. We can think about aerospace components, but also in oil platforms. And they're considered the workhorse of the process industry, so they're just expected to work. Unfortunately, though, we are in the Industry 4.0 revolution, but heat exchangers are subject to the same vibration issues, leakage issues, and fouling issues that they had since they started running more than 100 years ago. And one of the reasons of that is that we are relying on established design and monitoring methodologies. And so we don't really look, the heat exchangers have received very little attention as a part of this revolution because we expect them to work, we have established design and monitoring methodologies, and so why should we bother looking at them? Well, it is important to look at them, as I will explain in a second. So let me give you the example of the crude distillation unit. This is the first unit that the oil encounters when it's processed in a refinery. And what happens is that the oil, as it goes through the preheat train, a series of shell and tube heat exchangers typically, but with different technologies these days as well, what happens is that there are a number of chemical reactions and physical processes that happen that produces insoluble species that tend to deposit on the thermal surfaces of the heat exchangers. As a result, the heat transfer goes down and the pressure drops goes up. At the plant level, what we see is that we have a decrease in the inlet temperature of the furnace. And when we hit the limit, so therefore we need to burn more fuel to keep the distillation temperature high, which in turn emits more CO2. When we hit the furnace limits, then we cannot burn anymore. We need to throttle down production. And this is where we lose most of the money, really. In some cases, we increase the pressure drops. And by increasing the pressure drops, in some cases, we can hit the hydraulic limit, which means we cannot push through enough crude because of the hydraulic resistance of the network. So the throughput goes down, not because the furnace is constrained, but because the hydraulic limits is hit. So crude oil becomes, here you see a few pictures. I'm sure people in operation know very well what I'm talking about. It can become very hard and difficult to remove. And it creates operationally a very big issue. So it's not just economically, which I'll mention in a second, but also operationally, it becomes a very difficult problem. We need to extract the heat exchangers. We need to use high pressure 1,000 bars jet lances to remove the deposits from the units. This is a very significant problem, not just for individual refineries, but at the global scale. Just to give you an idea, it has been estimated that the extra CO2 emissions produced because of fouling in preheat trains worldwide is responsible for 2.5% of the CO2 emissions. So it's a very big problem environmentally. We have economic impact. For a small refinery, 100,000 barrels a day has been estimated about $10 million production loss. You can end up burning more than $1 million in extra fuel. And in fact, this is probably a conservative number from what we see. You need to have extra capital because you tend, the way that heat exchangers are designed, we tend to account for more area. So it becomes, we build bigger heat exchangers and so on. So, and something that people tend to forget is also the cleaning cost and the waste disposal costs, which are not really negligible. Now, if we need to go all through these issues, if you need to go through all the trouble of taking the bundles offline, having maintenance teams coming in, perhaps shut down parts of the plant, if not the entire plant, the first question we need to ask ourselves is why? Why should I clean? And in fact, a lot of people try to extend their run length as much as they can without having to go through cleaning. So the first reason is obviously to prevent unscheduled downtime. So avoid loss in production, unscheduled loss in production, but also scheduled loss in production. Because if I need to maintain on a regular basis, I need to shut down, lose production, and clean, right? In some cases, we want to maintain on-spec production, improve energy recovery and efficiency, decrease carbon emissions, as we have seen all the big impact that the fouling has in the preheat train, but also in other type of plants. The bottom line is that it's always convenient, really, to clean heat exchangers. If you actually do the right type of cleaning at the right time, it is convenient to clean. So that's really the reason why, besides all the other implications that I just mentioned, we should try to clean as much as we can in a smart way. So this is just to give you an idea, a case study that we ran some time ago, looking at 4 years run in our refinery, and I'll describe this a little bit more in detail later on. In this case, we had no cleaning. We built a digital twin for a refinery, and we look at what would have happened if the refinery did not do any cleaning. We looked at how much the refinery was able to save by doing cleanings with the simple heuristics that they already had, and what would have happened if they could optimize the cleaning actions. And you can see here from the summary table, and I'll go a little bit more in detail later on, but you can see that savings can add up significantly. So the refinery themselves, they saved about $2 million, but with our technology, we would have been able to save over $4.3 million by optimizing the type of cleaning that we're doing. Then there are other questions. Which unit should I clean? When I have a train of 30, 40, 50, 60 heat exchangers, which is the unit that I should clean to maximize my return on investment? When should I clean it? How should I clean it? Should I clean mechanically? Should I clean thermally? Should I clean mechanically, chemically? And how long should I clean for? How long should I take my heat exchanger offline and so on? So the problem is that all these questions don't have an answer because of the current maintenance philosophies. If you look at how maintenance is performed at the moment, we have what we call preventative maintenance. This is a picture that I took back in Houston airport when at the time we could still travel. In this case, maintenance is performed at regular intervals, which is exactly what we do with our car or what we do with our escalators, right? Then we have people that follow a reactive maintenance, where maintenance actions are only taken when operations are constrained. So that's what we call a run to failure. I keep operating until I hit a problem. I hit my furnace limit, I have throughput loss, then I start open up heat exchangers and clean. And then there is what I call the Mad Hatter approach that says that we cannot clean because if we clean, we need to stop and lose production. But the issue is that the reason why this is happening is because the plant itself is in a state where it cannot be cleaned effectively unless you lose production. But if you're able to understand when that happens, when you bring the plant to that point, and you can take actions before that point in a predictive way, that's where you can start planning to move away from this limit and have a more regular cleaning with more effective actions. In fact, it doesn't need to be this way. It doesn't need to be one of these three options. Now, thanks to the Industry 4.0 and the widespread adoption of sensors and data, we are able to run models that can connect to the plant and better conditions of the equipment, run optimization algorithms and predictive algorithms to provide better cleaning decisions to the operator. Now, this all hinges around being able to do this, being able to predictively understand when some problem is going to arise, is only hinges on the ability to be able to predict fouling. Okay, so if I'm able to predict fouling, I can look forward and understand what is going to happen and what actions to take in order to prevent any of the losses that I mentioned before. The problem is that fouling predictions are not easy. They are not easy because they are system specific. They depends on the fluid, on the process conditions, on the surface conditions, for example. There are several complex and interacting phenomena going on. And trust me, we have tried to understand these phenomena. We have been doing experiments, we've been doing analysis, and it's not an easy problem, particularly for crude oil, because the components are so many, and the deposits that you collect when you analyze them have changed so much from what caused the deposition, that makes this problem very difficult to crack. Also, there are some indicators traditionally used in refineries that can be misleading. And one of them is, for example, the fouling resistance. And I have a whole other discussion. We can have a whole other discussion about this and why fouling resistance could be misleading. And also plant measurements. We do live in the era of Industry 4.0, but we did see that some plants are very old. And these plants were not designed to allow for so many measurements. So even if wireless sensors allow connectivity to the DCS, for example, in a very cheap way, you might not have the ports in the heat exchangers to be able to put the sensors. So the quality of the measurements and the availability of the measurements is also a problem. And to me, it's also, there is a general lack of system approach. We are looking at the problem in individual heat exchangers. We're not looking at the problem at the network level. So the summary of this is really the AI plug and play doesn't work. The complexity of the problem is such that one is tempted to say, let's throw artificial intelligence to the problem and see what happens. But the reality of it is that the information is so little and the phenomena are so complex that this cannot, AI alone does not work. So what do? What we look at is looking at hybrid models where we have we nail down the deterministic process as much as we can, and we have artificial intelligence to support the deterministic models to provide the right state of a heat exchanger and to provide better predictions on for the future. So the key thing here is that we capture both the hydraulic and the thermal aspects of a preheat train, for example, in our digital twin, which means that we can capture simultaneously the effect that fouling has on temperature, so the furnace limitations, but also the hydraulics, so the pumping problems. We also look at composition and being able to predict the type of fouling based on, and the fouling behavior based on the composition of the oils. That's a very challenging problem, but with this approach, it's possible. So, and then of course, we can also look at design for no fouling conditions and so on and so forth. So to overcome the limitations of the around the fouling predictions, we have seen that this approach works quite well. The benefits is what really goes again to my initial point. Really encompasses the production problems, the reduced fuel, allows to reduce the fuel consumption, provide effective maintenance, and so on. For the sake of time, I'll just move on to the case study. Very quickly as well, I'll just brush over this, but if you're interested, you're welcome to contact me, and I'd be happy to go more in detail with this. This was a refinery that was already very, very well run, and a crude slate change every 2 days, and we were running opportunity crudes. What we did here is with the same example that I showed you before. So we did the digital twin, and we looked at the performance of the existing maintenance philosophy together with the performance of what would have happened if you did not have any cleaning, just to have an idea on how important it is to clean on a regular basis. But then we went a step forward and we looked at how can we optimize the performance of the network and the cleaning actions together with, for example, in this case, the flow split operations. So while I'm doing my cleanings, can I maximize, can I send more fluid on one side or the other of the two branches so that I balance my enthalpy of the furnace to maximize the energy recovery. But we do this taking into account the long-term effect of fouling. So the combined optimization of the flow split together with the cleaning schedules resulted in 4.3 million, over $1 million a year savings. Okay. As I said, this is very quickly. I'd be happy to go more in detail if you're interested. So this leads to my conclusions. Prescriptive maintenance of heat exchanger networks drives operational excellence, unlocking increased production, savings due to reduced fuel consumption, and cut of CO2 emissions. So also from an environmental point of view, it's very important. Our approach with hybrid digital twins that incorporate AI with high fidelity models are key enablers in tapping into these benefits. And low cost and low risk options can be implemented with very low or no capex and a clear return on investment. I'll be very happy now to take any questions, and you're very welcome to contact me, of course, offline anytime you'd like to. Thank you very much.